This video is going to work through the example starting on 1-10 of the course pack. It's an axial loading problem. Problem statement: find the maximum stress within the steel bar and the total length change when the loads are applied. The dimensions are given in millimeters. Use a Young's modulus of 200 gigapascal. Alright, the problem statement tells us a few things right off the bat. Total length change, so total deformation is going to equal the deformation of the two smaller parts, so that within section AB and that within section BC. And we're looking for maximum stress, which means we're going to have to find the stress in this segment and that segment and compare them to see which one is in fact greater. So to start out, it's never a bad idea to do a free body diagram and figure out all of the external forces acting on a structure. So we know we've got 150,000 newtons, 75,000 newtons, and we know that we've got a reaction force that's going to happen in the x direction. Sum of the forces in x always equals 0, plus ax plus 150,000 plus 75,000 equals 0. We see that ax has to equal minus 225,000 newtons. That negative in this case is just saying that the sense of our reaction force is drawn incorrectly. So the actual state of affairs is a 225,000 newton force this way, 150,000 newtons at the diameter change, and 75,000 newtons on the free end. So we've established all of our external forces. It's always a good idea to remind ourselves of what the base units that we're working in, and to stay consistent with your metric prefixes, giga, kilo, or what have you. Now, in order to figure out what the maximum is, we need to know what the stress is in each segment, which means we need to know what the internal force is in each segment. We can go about that by taking a section cut and looking at the remainder of the structure on either side of the cut. So for section AB, a free body diagram of the part to the left of the cut. We know we have the reaction force of 225,000, and we have an unknown internal force we call P sub AB. With only one force going on, such a free body diagram seems trivial, but for thoroughness and to keep things clear as the problems get more complicated, it's always a good idea to go back to the basics and do the free body diagram. From here, we write the equilibrium equations. The sum of the forces in X is equal to a minus 225,000 plus PAB. Tells us that PAB is equal to 225,000 newtons, and the fact that this right here is pointed away from the cut face tells us that this internal force is a tension force. So, in order to get the stress within section AB, we need the load, our internal force within section AB, and the area of section AB. We know that our load is 225,000, and our area, pi over 4 times the diameter squared, 225,000. The diameter was given as 35 millimeters. Converts to 0.035 meters. So 225,000 newtons over 9.621 times 10 to the minus 4 meters squared. That yields the fact that the stress in segment AB is 2.339 times 10 to the 8th newtons per meter squared. Converting that out to standard metric units, we have 234 megapascal. So that's our stress in section AB. All right. Having determined that the stress in segment AB is 234 megapascals, we now need to determine what the deformation in AB is. Deformation is our delta sub AB. Generally, deformation is the product of the load, P, internal force, P, times the length of the segment, divided by the cross-sectional area of the segment times Young's modulus. Now, when you have multiple cross-sections, you have to consider that the different cross-sections may have different quantities. We already know that our internal force, PAB, is 225,000. The length of the segment, given on the initial drawing, is 400 millimeters. But for consistency of units, we're going to convert everything and do math with base units. So that's 0.4 meters. Our cross-sectional area that we calculated while getting the stress, and the Young's modulus is given in the problem statement as 200 times 10 to the 9 Pascal. So, given all of these quantities, substituting in the deformation in AB, 225,000, 0.4 meters, 9.6211 meters squared, 200 times 10 to the 9 Pascal, and the trusty calculator will tell you that this is 0.000468 meters, which is also equal to 0.468 millimeters. Now, we figured out the stress in segment AB, as well as the deformation of segment AB. Now we have to look at what's going on within segment BC. There's two ways that we can do this, and the math will always work out correct. We need the internal force P sub BC. You can take your section cut and evaluate everything to the right of the cut, or everything to the left of the cut. To the left of the cut is the reaction force of 225,000 and the applied force at point B of 150,000. Alternatively, if we evaluate everything to the right of the cut, we have the smaller segment of the structure, and we have only the 75,000 Newton force. In either case, the math will give you the correct internal force. The problem is much simpler if you choose to do the part of the structure that's to the right hand side of the face, of the cut face. Now, having chosen to use the portion of the structure to the right hand side of the cut in section BC, we can do our free body diagram of that portion of structure. We know we've got the 75,000 applied load, making the assumption that the internal force is a tension force. We draw the internal force PBC pointed away from the cut face. We write our equilibrium equation in the x direction. We have a negative PBC plus our 75,000 equals 0. PBC is equal to 75,000 newtons, and the fact that the positive sign coming out of the equilibrium equation matches the direction indicated, and the fact that the direction is pointed away from the cut face tells us that that internal force is a tension force. So, now that we have the internal force, we can find the stress in this section BC. Sigma BC is equal to the internal force divided by the area, where the area equals pi over 4 times the diameter squared. The diameter in this section is 0.02 of a meter. So the internal stress, 75,000 divided by and that math ends up being 2.387 times 10 to the 8 Newton per meter squared. Converting to standard metric prefixes, 239 megapascal. Now we want to determine the deformation. In section BC, generally that's PL over AE, so we need P, the internal load, except not in AB. We need in BC, we need the length of the segment BC, the cross-sectional area of BC, and the Young's modulus of BC. We know that this is our 75,000 newtons. The length is 300 millimeters. Convert to meters. The area (3.1416 times 10 to the minus 4 meters squared), and the Young's modulus of 200 gigapascal. That ends up with a deformation of 0.000358 meters, or 0.358 millimeters. Now, overall deformation depends on what happens in the larger segment and what happens in the skinnier segment. So from the earlier part of the problem, the deformation of section AB is 0.468 millimeters. We just determined this deformation is 0.358 for an overall deformation of almost a millimeter. In terms of the overall maximum shear stress, the stress in segment AB was 234 megapascals. The stress in segment BC is 239 megapascal, indicating that the maximum normal stress is in the smaller segment with 239 megapascals.